Hello, everybody. Good morning. We're starting with our session on infrastructure and tools. In this session, we will have 5 talks. Each talk is 10 minutes and 2 minutes Q&A, as always. There are mics around the room, so if you have a question after the talk, just raise your hand. And with that, I already want to invite Christina Bukas on stage. She's a Helmholtz AI consultant in Munich in the area of health and works on biomedical imaging, especially with noisy labels. Looking forward to your talk.
Thank you for the kind introduction. Good morning, everyone. Today I'll be talking to you about AI-assisted labeling and its pitfalls with a case study in electron microscopy segmentation. So, let's get started. We all know that high-quality labels are essential in many machine learning tasks, and this is also true in my domain, so biomedical imaging. And in the last years, AI-assisted annotation has been a promising pipeline, which allows for faster data annotation. The standard workflow will typically involve starting off with, let's see if this works, your data here, followed by a foundation model, typically to acquire what we call pre-labels. And then that would be followed by a human expert for manual curation. Sorry, I don't know how to get rid of the laser once I start with it. And then typically you would go back to your data and either continue in a human-in-the-loop fashion or then have your curated data set which you can use for a further downstream task. So what we are doing in this work is tackling the problem of what we called mixed label sets, which appear in this standard AI-assisted workflow. So mixed label sets, we mean basically a mix of human-generated and model-generated labels. And what we argue is that such a pipeline can introduce batch effects into the data, which come from this mix of labels. And we are proposing a workflow where we correct for this batch effect with a mitigation strategy. So for our use case, we use a 2D transmission electron microscopy dataset. We collected 277 TEM images of mitochondria in healthy and diseased states, and this results in a dataset of over 8,000 mitochondria. This is an example of a TEM image here. You can see the mitochondria are these little structures here. And our task is to segment the mitochondria, which can allow for further downstream analysis. You see a segmentation example here. And to annotate the data, we are using BATS. Now, BATS is an open source bioimaging annotation tool for segmentation, which was developed in-house in our team. And before I go into detail about what we did for this project, I want to give you a quick intro into the tool itself. So, our tool, BATS, was built with a flexible client-server architecture. On the client side, we have it running on the user's machine, and it handles all data management tasks, and also manual curation of the segmentation data is done via the Napari API. The server is hosted either locally or remotely. We also offer model serving via the Bento ML API, which basically handles HTTP requests. And for now, we have a pre-trained cell-pose model, but it's quite easy to add also other models in the backend. It has several features, so we can handle all types of segmentation tasks, instance, semantic, and multi-class instance segmentation. We also have an AI-assisted labeling feature, which allows for faster data curation. This is basically the option for the user to add box prompts or point prompts in order to prompt the SAN model and get a faster curated label. And we also built it with data-centric practices in mind. So there is the option to detect and remove outliers from your data. There is the checks for detecting and correcting labeling errors by the user. Several automatic cleanup steps which run when the user saves the data. And finally, the option for multiple annotators via an established consensus scheme. And finally, we also have the option to extract useful features from the final curated masks. So just a quick intro demo here. This is our welcome window. Basically here you just set your data paths And this is our main window. On the left here, you see the list of uncurated data. We usually typically start off with this folder being full. If you hit your generate labels button at the bottom, you will run the pre-labeling model, in our case Cellpose, to generate the pre-labels for the mask. And then the user needs to go through these images one by one and curate them. When they are ready, they will be moved here to the curated data set. And finally, when you're ready, you can extract features basically for all data which is in your curated data. And this is the viewer, which the user used to curate the data. So it's a classic Napari viewer. On the top, you have your control panel where you can erase, paint, etc. This here is the AI-assisted labeling feature I mentioned earlier. So if you toggle that, then you can do box prompts and point prompts for helping with your segmentation, and basically functions on the bottom to save the data and do the checks. So that was the tool that we use. And going back to our case study, as I mentioned, for the standard workflow, we used bats for annotating our data. And this involves pre-labeling with the Cellpose model, followed by manual correction by an expert biologist. And in our proposed workflow, we used the masks which were obtained from the previous step to compute bounding boxes around each single object, and then used these as prompts to the SAM2 model in order to get objects which are all outputs of the SAM2 model. So for our standard workflow, we track the instance origin. This basically means that our data now, all objects in our data can come from 3 different sources, either untouched, which means that they are objects which are direct outputs of the pre-labeling Cellpose model and were not edited by the user. Corrected, which means basically that they were outputs of the Cellpose model, which then the human annotator corrected, and added, which means that the model did not detect this object, but the user added it themselves later on. And from our standard workflow, we get then our mixed label set, whereas from the proposed workflow, we get our harmonized label set, which all outputs come from the same source basically here. And as I mentioned, having a curated data set then allows us to do further downstream tasks. So the first thing we did was feature analysis using the segmentation masks that we obtained. So from our masks, we extracted various shape-related features such as eccentricity and circularity, roundness and solidity, and plotted those. And you can already see here on the left particularly, it's very evident that based on the source of origin of our masks, we have 3 very distinct curves for the circularity. So our added instances, our corrected instances, and our untouched instances, our corrected instances, and our added instances. What is interesting is also that the corrected ones, so basically the mix of human and model, fall in between the pure human and the pure model generated masks. So yeah, this basically confirms our statement of how batch effect gets introduced when you have mixed label sets such as these. And when we do the same thing for our harmonized features, we see that the batch effect is disappearing now. So our mitigation strategies seem to work. We did an additional downstream task, which is quite obvious. That would be to fine-tune the Cellpose model with our data. And you can see an example here of the mixed labels that we start off with, and the harmonized labels, as well as the model outputs for each of the 2 data sets. So this is the results on the test set. Both models were trained with the same conditions. And I hope it's clear for you, because we are talking about details on the border of the objects, but you can see how in the mixed labels we have a bit of tendency on the borders to over-segment the border of the object. So you can see that a little bit down here and on the top there. And then I will remove the pointer because you have the arrows, which are hopefully enough. And then you can see also that the mixed model is carrying up these effects and doing basically also over-segmentation and under-segmentation in the border. Same holds true in this image here, and the last example that we have here. We also performed some quantitative evaluation on the border of objects and saw that we have a consistently higher performance for the harmonized labels. So to summarize, what we want to point out here is that annotating using a foundation model to pre-label our data, followed by a manual curation, can carry batch effects, which are introduced by mixing model-generated and human-added labels. In our case, these effects, as we saw, were particularly related to shape-related features, particularly on the objects of the border, and affected downstream tasks. So we just want to advocate that care must be taken to study for and correct for any possible batch effects when you're using mixed label data. We used the SAM2 model to mitigate the batch effects, and it worked pretty well in our case, but of course one can also explore further mitigation strategies and do that on a wider range of data. Thank you very much.
Thanks a lot. We have time for one question. There's one. The mic is coming there.
Thanks a lot for the presentation. How much would you need to add or develop in order to apply your toolbox to a completely different domain?
In theory, it could work in different domains, but it hasn't been tested, so it depends on the domain itself. So if we're talking about Earth observation, for example, where I guess you work with very large images, we would have to see how performance and latency would work in that case, because we haven't tried it out yet. So our image is like 2000 by 2000 pixels, and it works well, but yeah, I don't know if you would have to adjust the way you do inference, for example, on such large images. But in theory, it should be possible. Thank you.
All right, let's thank Christina again. The next speaker